David earned his PhD from McGill University in 1993. He works in really a wide range of aspects of geophysical fluid dynamics, and most recently he's been working on applying this to interactions with the ocean-ice interface. And another example of someone who's worked in different disciplines here, he's going to tell us probably a little bit about his modeling work, but also some observations he's been doing as well. And so we're very pleased to have David here.
Thank you, Andrew. So following on from Anna's talk, I'm going to zoom in on the ice-ocean interface. Really, the purpose of this talk is to discuss the formulation of melting, the equations we use for that, and some different examples of warm water regimes, cold water regimes, and other regimes. So a bit of the big picture is, in front of these ice shelves you have either cold water or warm water, and that really comes from this kind of big picture. So the really big picture is not so difficult to understand. The atmospheric variability in the north, the North Atlantic Oscillation, and in the south, Southern Annular Mode, basically are two modes of atmospheric variability that have an enormous impact on the conveyor belt and the currents near Greenland and Antarctica. These variability, which we're not going to talk about, somebody was asking about the sea ice earlier, this emanates from the tropical regions where Rossby waves emanate out, impact on these modes, and cause apparently much of the variability which we see. So there's this picture. It's kind of the big picture. We've seen in the 90s parts of the Erminger current coming along, changing direction around Greenland. We haven't seen such around Antarctica, probably because we don't have the data sets to see it. But it's kind of, this is the big picture Anna was showing, the ACC going around Antarctica. And part of what Anna said was that in some places we have warm water, in some places we have cold water. So those are the two melting regimes I'd like to look at in detail. But there's a third regime, and that is the water that comes from the glacier. So we have three water masses that show up at an ice-ocean interface. Warm CDW, cold high salinity shelf water, or its equivalent, or possibly the impact of subglacial water. And all three of those have an important impact on how ice melts. Page down. Another picture to bring out, this talk is kind of Antarctica and Greenland. I do want to emphasize that people who think about these two regions, they are very different in one sense, and that's simply the scale. The Antarctic outlet glaciers are enormous, and the Greenland ones, even the celebrated Jakobshavn, on scale are much, much smaller. It's much more difficult for the ocean to interact with Greenland than Antarctica. So personally, I take Greenland as an interesting place, but I take Antarctica to be a more important place in terms of the questions we are addressing these days. The three regimes we're going to look at: a cold water regime from the McMurdo ice shelf, a warm water from Pine Island Glacier, and a glacial water place, Jakobshavn. Some of the names that most of you know, but in case you don't, basically the words we're using are flashing on the screen, and you can follow them without me saying them. In the Southern Ocean, again, it's the CDW, this warm water that does float stably in the ocean. The equation of state for water, it's empirical, and at cold temperatures, salinity dominates. That's a stable configuration. In the north, it's the same story, except in the Arctic Ocean, it's the Atlantic waters, or around Greenland, the Erminger and derived water masses. Again, very stable. So it's this picture you should keep in mind, that this stuff is born in the polar regions, the Arctic or the Antarctic, polar surface waters. This comes from the tropics and subtropics, and this is, again, polar. And it's the way these are just empirically interleaved, but they are all happily stratified in density. High salinity shelf water, ice shelf water. For the Greenland part, I want to bring out this part. Many of you have seen nice pictures of moulins. Originally, I didn't think moulins and or their contribution to subglacial meltwater would have much to do with anything, but it is possible that, in a nutshell, these water masses slip out and actually accelerate the ocean circulation in and out of these cavities. So what I'm interested in is, Anna talked about the continental shelf. I'm talking about this actual interface. And there's two parts to this problem. The easy part, called ocean thermodynamics, and the hard part, called ice dynamics, which I'm not going to talk about. So this is the easier part, basal melting. How does it happen? it happens ultimately by molecular exchange. So it's a solid boundary meeting with a liquid. So exchange is not turbulent. At the final delivery point, this occurs by molecular exchange. And those of you familiar, heat and salt diffuse at different rates. So there's a complication there that really matters. This is a busy diagram. Originally, I didn't like this nomenclature, but I've become more of a fan of it. So aside from all the words on this diagram, just pull out these three for the moment. Mode 1, meaning water that is formed on the continental shelf, high salinity shelf water. It forms here, and it's called mode 1. It interacts. It's very cold. Mode 2 does not form on the continental shelf. It comes from the subtropics, etc., or elsewhere, and it's warm. That's the warm mode. And the other one is mode 3, which is this little curious thing where water locally from the surface can interact with the ice shelf, and we'll mention that. And that's another cold water. Here's a hard problem, ice front calving. It has been estimated that half of the ice loss from Antarctica and Greenland, in a ballpark, comes from calving. Physically, what it seems to be is that we've spent a lot of energy on ice ocean thermodynamics, not so much on calving. In my view, there are only a half dozen theories at best out there for calving. I attended a workshop on this last year, and basically I'd say it's a field that needs a lot more work. But again, I will talk to you about thermodynamics, melting, but I'm ignoring half the problem, which is ice simply breaks off and floats away, and we don't really have good models for that or observations. Calving, those of you seeing this video from Jason Amundsen, this is where I work in Greenland. I've gone there 5 years. I've never seen this, but I landed there in a half hour before this had happened, and Jason, a student, had photographed this. This is the kind of event that is half the contribution, and it's ice fracture dynamics with some possible contribution from oceanography. So what is the melting part? Basically, in the 80s was the decade of sea ice, where people formulated equations, largely Miles McPhee, about how sea ice melts. In the 90s, the ice shelf community took that information and transferred it over to the ice shelf ocean problem. So do you get that? So sea ice, really well observed, studied, and then it was brought over into this ice shelf world and really never verified at the beginning, but certainly steps have been made since then. The reason I'm going to show you some equations in math, because pretty much every paper you now see will have this statement about these equations, the so-called 3-equation model. Some use 2, and virtually no one uses the 1-equation model anymore. And I'll tell you what those 3 equations are. But basically, they're worth going through because sprinkled throughout the literature are always these equations and the different parts and ways people interpret them. So it's quite simple. You have ice and you have water. This is the ocean mix layer. And this is very turbulent. This is not. But the transition zone between ice and water, if you really zoomed in there, it would all become molecular. There is no turbulence in the last few millimeters, the so-called viscous sublayer. And I'll show you how you can estimate the thickness of that. It's of the order of a few millimeters. What is so difficult about this is, we'll get to that, but what at least should be obvious is if I want to know the melting of that interface, I just need to conserve heat, conserve mass, conserve salinity. But I also have to behave an empirical formula, which is the latent heat formula. That is, the change from liquid to solid is the freezing point relation. It's completely empirical, and it depends on salinity, it depends on pressure. So again, most of us are used to think conserve mass, conserve momentum, conserve salt. Well, here you have to have that one other principle that is, if you will, obey the freezing point relation. Jumping back to the thickness of this layer, so people like to speak about a friction velocity. The ocean mix layer velocity, I'll call it UM. People use a coefficient of drag, which is empirical, and they come up with something called a friction velocity. Just raise that. And the way you scale the thickness of this molecular sublayer is from the viscosity of water divided by the friction velocity as a scale. And if you plug in standard numbers for that, you'll come out with millimeters. And in that little layer, heat and salt are diffusing quite differently. Salt is diffusing very slowly. And salt is a key player in the freezing point. So this is the freezing point relation. The freezing point depends, essentially linear, on the salinity and the pressure. And the pressures can be large. You can be down 1 kilometer or 2 in ice, and as you increase pressure, you decrease freezing point by about a degree per kilometer. And in ocean, this effect is huge. This is like 2 degrees of impact, and this is like a degree. So we have to behave to that relation. And what I want to stress there is if I'm trying to compute the freezing point, this is the salinity here at this little interface, not the salinity of the bulk ocean. And these can be quite different. And as far as I'm aware, this is where the theory starts to become less rigorous, in the sense that I'm unaware of that people have made detailed measurements of this mythical, magical viscous boundary layer. But yet its impact is quite important. So conservation of heat, the heat conducting through the ice, this part, minus the heat coming from ocean turbulence. The difference is the melting. What about the heat coming from the ocean? This is a traditional formula where you just say a heat flux from the ocean to the ice is a temperature gradient, dt dz. But you can't know this temperature gradient because you don't know the temperature precisely at the boundary, at the ice-ocean interface. You don't know that temperature because you don't know the salinity at the interface. So you don't know it. So what people have done instead is this idea where they've, instead of getting this gradient, Tm dz, right at that boundary layer in that last 5 millimeters, okay, you get it? Heat flux, temperature gradient. It's that boundary temperature in the last 5 millimeters. They say, oh, that's maybe a little too difficult. We'll try to parameterize. They say, what about if I got the temperature difference between the base and the mixed layer? So this broad temperature gradient over the scale of 10 meters instead of 5 millimeters. And then they say, well, okay, so those of you familiar with that, there's a parameter, which is the ratio between the temperature in the molecular sublayer to the temperature gradient in the big boundary layer, Nusselt number. That doesn't help you. That's just, again, a parameter. And so people say, okay, we can do that. And finally, what they do is they say, well, why don't we just call this whole thing gamma t, and why don't we go measure it and just see if we can empirically get away with this. Do you see how we've swept away quite a bit here? And then those of you familiar with gamma t has a really complex dependence going back 30 years, but I'm not sure verified since it was originally done in engineering fluids labs. People also like to make this the product of another empirical parameter and the friction velocity thing I talked to you about earlier. And then that becomes Stanton number times friction velocity instead of gamma t. That's called an exchange coefficient. And that is really the end of that little story. So, and then the other part is salt fluxes. You can do the same formulation, except you can say, I want to bring salt from the mixed layer into the interface, and then you have this gamma salt. And so finally, let's take it to the final point where people have brought this. This is, going back to engineering fluid dynamics, these exchange coefficients, this is their formulation. Friction velocity divided by these other gammas. One due to turbulence, one due to molecular diffusion. I'm not going to explain these, and you can read all these numbers and that. And you say, oh my gosh, what is all this stuff? Well, it's stuff people have measured between Coriolis parameters, sublayer viscosity thickness, empirical parameters, stability parameters, blah, blah, blah. The point of that, and there's the stability parameter, is that is currently what is used pretty much in every ice-ocean modeling effort recently. And some of it has been verified by observations, and I'll show you a few cases of that. My concern would be, one is that I would like to see all of this theory redone from a laboratory perspective, and to see really just, I'm not completely convinced of it. It seems to be a lot of jumps of empirical statements that end up with these formulations. So let's jump. So that little bit of theory is how you come up with the melt rates. This is the ice pump, mode 1, we talked about. Right now, I'm going to jump to a little bit of mode 3. This is work done by a graduate student who put in a measuring device right here at Windless Bight. And the idea is, can you make year-round measurements here under an ice shelf to see mode 1 melting? And can you make measurements of melt rate? And are they equivalent to that formula? Well, we come up a little bit short here because of the technology we employed only gave us temperature data, and we were unable to get salinity data. So just one second. Okay. This is a computer simulation showing, from Mike Dinneman, showing around Windless, Bight, and McMurdo. In the summer, warm waters come along here when the Ross Polynya opens, and waters come in around here, shallow at Windless, Bight, driving the melt rates up substantially. We wanted to observe that, so one of the technologies we employed was to put in fiber optic cables about 1 kilometer long, and they can measure temperature every meter near constantly, kind of in this cartoon. This part here, that's a numerical model from Mike Dinneman of a snapshot time series underneath Windless, Bight, time running along the bottom. And that's from the fiber optic cable. So at one level, I'd have to say that's pretty good, actually, that we can make direct measurements under ice shelf cavities of temperature signals. You could imagine, if one had the interest and energy, to deploy an armada or an array of these temperature sensing devices, and you could monitor ice shelves continuously with this in terms of temperature. It is a little bit more tricky to get salinity. Those of you who follow optical fiber technology, they can measure speed of sound, so you can measure sound speed, temperature, and infer salinity, but I don't think you can do that accurately enough yet. So, jumping back to this equation, when people say they're using the 2-equation formulation or the 3, what they mean is, in the 2-equation formulation, you ignore salinity. You just say, I'm going to study the temperature, thermodynamics, and the freezing point, right? Freezing point, 1 equation. Conserve heat, 2 equations. So just use that and ignore salinity, meaning that you think salt diffuses from the mix layer to the base of the ice shelf instantly. So that's the 2-equation formulation. And the problem with that is that you can tune it to work for certain temperatures of water, but you can't get it to work more generally. So the 2-equation just says, I will conserve heat. That's that statement. Turbulent heat flux equals melting. People have rewritten that in terms of Stanton numbers I mentioned. Fair enough. And there's the melt rate. So with the 2-equation formulation, you can come up with a melt rate. But again, always remember that the math looks fine, but there's always this empirical parameter, which you don't know if it's a constant or not. Here it's the Stanton number. This may look really bad in terms of this blue line here is the modeled melt rate at a point under the Ross ice shelf. And the red is the 2-equation melt rate from the fiber optic observation. And you would say, well, that looks the same. It looks like the fiber optic missed this. Well, it didn't. It captured a large signal of warm water arriving under the Ross ice shelf. But the gap between modeling and observations is huge. This is not to say the models are bad or the observations are bad, because there's a question on both of these. This is to say that the gap is really big. So when you look at a plot in a model of a melt rate, we are still a good ways away from being able to say that we have high confidence in what we are modeling. And you can play with sensitivities, all the things you're not sure about in the model, and you can come up with numbers that always make you a little uncomfortable on the scale of as much as 50% in melt rate. Jumping from a cold place like the Ross to a warm place like Pine Island, one of the things that seems to change is warm water melting seems to cause channels, just like riverbeds on land. At the base of an ice shelf, as far as I can tell, in warm ice shelves that I've looked at, or ice shelves that have warm water, there are these channels. So you can see these in the PIG from a digital elevation map. And they're enormous, 3 or 4 kilometers wide and 100 meters of melt in these channels. This is a little place area flown over by a radar. And this is a computer model by a student who took a glacier model and a mixed layer ocean model and just put warm water in. And got channels to occur. And it's still even not clear after this work really what sets the scale width of these channels, which appear to be in nature about 2 or 3 kilometers. We effectively, in the end, had to put in all these different patterns of possible melting and see what the ice shelf liked to select. But we still didn't really take it all the way home to say, why is it the channels form? I can tell you, once you grow them at the grounding line, then this physics that we do know about takes off and takes it home. So how did we arrive at that? This is the 3-equation model. So as I said, the 2-equation model, you ignore salinity. The 3-equation one, you have the freezing point relation, and then you have these 2 equations: conserve heat, conserve salt. And that, again, are those exchange coefficients with all those magical parameters in them. The first panel is, this is an ice shelf. There's the grounding line. We made little cuts in the grounding line and then put warm water in. And the ice shelf, which was originally flat, developed all these channels. So this red is the ice draft, where it's deep. This is the melt rate, which can get as high as 60, 70 meters in these channels. And then there is the channel depth there. What's interesting about channelization at the base of an ice shelf is that it causes an ice shelf to melt less than it would if you didn't have channels. You would think there's more surface area in a channelized surface and it would melt more, but in fact it melts less. That was the modeling work for the Pine Island Glacier. Tim Stanton has led an effort for the last 7 years, kind of Herculean, in order to get measurements under PIG from direct in situ measurements. You know, the autosub went underneath, but this is more of a mooring approach on this ice shelf. And our little camp in January is that little scratch from space. Can you see that? That's our little snowmobile tracks going on. And we put in 3 drill sites, ABC. The drama of Antarctic science compared to Greenland science, to me, is huge, in the sense that in Greenland you can go as a researcher and do research. In Antarctica you simply cannot decide, you will just simply go there and do research. And to get a hole drilled, in the end, to put in a CTD took 7 years and involved crazy things like dismantling helicopters to put them inside Herc airplanes to get them onto an ice shelf. So observations are coming slow, and I'm not sure that's going to change fast in the future. Anyway, fast forward 7 years, and you can measure some of these parameters in this 3-equation model. You can measure the currents underneath, the friction velocity, which is kind of the stress, the departure from freezing, and look at that number, that's 1.4 Kelvin. So finally we have observations beneath an ice shelf to validate this 3-equation model in a warm water regime. So that's not 0.1 Kelvin, that's 1.4 Kelvin. And finally you have the salt flux. So Tim put in a device that measures temperature, salinity, and velocities 4 times a second, so you can get the fluxes, the actual W prime, S primes. So you can actually take the conservation of salt equation, which is W prime, S prime, ocean salt flux equals freshwater flux, and solve for the melt rate directly, which he did. This is just for sanity check. An altimeter was put in, and this is just the first month, and you can see the ice is melting, indicated by this line going up here. So the altimeter measured this red information, which is a certain melt rate, 6 centimeters a day, which is enormous. And the blue comes from effectively the modeling, if you will. And so you can decide yourself whether that's good or bad, but arguably that's the truth, the red. And the model is the 3-equation model. It's close. And why there's a gap, you and I and all of us have to think about further. But suffice it to say, well, you can make your own judgment whether that's good or not. Finally, that was a cold water and a warm water regime. There is this other regime, which is this, certainly appears to happen in Jakobshavn. It might happen in other places. This is an old NASA animation, just to give you a sense of where this glacier is. And you can fast forward. This calving front has moved back a lot in the last decade. There used to be an ice tongue, which has since destroyed, and now it's calved all the way back even to here. This is rock now over here. we've been trying to understand this fjord, this is, and why it is that it has warm water in it and how it flushes. And it's a funny story in terms of one that would not be obvious to me, but we've been measuring out in front, CTD. You can do that quite easily from a boat. This is in Greenland, as I said. Research is not so difficult. You can just charter a boat, put a CTD on it on the scale of 2 or 3 people, and off you go. So what we've been seeing from these CTD measurements at the mouth is that every year different water properties show up at the mouth of this fjord. Not little changes, big changes. So we've been able to record that. Getting into the fjord, it's a little bit more difficult. We've also put moorings there, and the moorings have been problematic for a number of reasons. One is that fishermen keep dragging them up, and I don't know if they're doing that on purpose or not, but they get a ransom for returning them. And that's fine. In the fjord itself, we've been doing probe drops. This has turned out to be a fair amount of fun. I like this part in terms of the beauty of some of the scenery around these glaciers is really quite awesome. The goal here is to find little holes in the ice in which you can put these airborne probes. And every now and then we find holes. Some have been made by seals, and if so, then you can drop probes about this scale into these holes. And the pilots are very good at using the rotor blades to actually force open the holes at low altitude. So those probe drops have been working fine. And there's another kind of probe, which is a bigger one, which we started experimenting with this summer. And these are the, not temperature probes, but this probe actually gives you the current. It can use the Earth's magnetic field and give you the current. And now we're seeing in the fjord the water current profiles, which is adding a whole new dimension to the story. And seal tagging. We've been tagging seals in this fjord. People have been doing this in Antarctica for the last decade or so. This is a fabulous technology, and probably in the end it's going to be the winner technology. These seals, locals put the CTDs on them. They phone 4 times a day. Every now and then they dive very deep, 500-600 meters, well into the Atlantic layer waters. And so that data set. And there's the seal data set. And if you pick the right seals, they'll stay where you think they might stay. Combining those data sets, what we see is, so this is the glacier on this side. Here's the mouth of the fjord. This is, I don't know, 60, 70 kilometers the fjord. Basically, in this year, 2009, the fjord is warm. In 2010, it completely flushed. It was cold. And the next year, it was warm again. So this fjord renews and changes temperature significantly on interannual timescales. It might do so quicker. And the question we had is, but it has a big sill. So how does water keep going in here? Like, once you fill this with dense water, why would lighter water come along and replace dense water? And it does. And the answer is subglacial hydrology. So we played with a model, and what we found is that if you shoot fresh water in here at the bottom, that fjord will flush. And if you don't, it won't. That doesn't mean that what I'm saying is correct. It's a suggestion that, in fact, the flushing of this fjord depends on subglacial hydrology, and that means the melting and of the actual calving front depends on that. Here's a computer simulation just to partly show you that, but I'll just jump through it. We start off with putting our observed temperatures in, and then we inject fresh water at the bottom near the calving front, and it causes a circulation that eventually causes this fjord to flush. That water is yellow-orange. It's warm, and then subsequently, I'll just jump ahead a bit. Well, I'll jump too fast. But anyway, it flushed. You can use your imagination to fill the rest in. So the summary is, what I would say is that for thinking about melting of ice, there is the cold water regime, and that's just the classic ice pump. The warm water regime is quite different, where you have to begin to start paying attention to the fact that the ice shelf base becomes corrugated, channelized, and the melting happens in those channels. And in some cases, I would suggest that thinking about subglacial water is also relevant in terms of my cautionary statement would be that the melting in Jakobshavn is dependent on that. I wouldn't bet my life on it, but from what I've seen from the modeling, it looks to be the case. From what I've seen from observation, well, without question, the fjord does flush. The half of the problem that I ignored is the ice front calving, and that is something where people need to pick up the ball in terms of fracture mechanics and figuring out how does ice calve. I suspect basal melting is tied in with ice front calving in that really particularly in the warm water regimes. And the final thing in the last 27 seconds is within these things, I'd like to leave you with that idea that we do have what I call a 3-equation system, one that involves conservation of heat, salt, and the freezing point relation. And I believe that is the most accurate relation we can use. It's still not perfect, but from Pine Island in a warm water regime, we've seen it behave fairly well, where we made direct measurements. Here in McMurdo and elsewhere, fairly well. So I'd leave you with that, and that's it. 5 seconds. What can we talk about?